welcome to QLab. In today's video we're going to be measuring friction. But what is friction? Well, let's have a look. Friction is a reaction force. But what is a reaction force? Well, if I had a block on a table, there would be a number of forces acting on it, such as gravity, which results in it having a weight, and we can see that pulling down on the block. But the block isn't going through the table, so we know that there must be another force acting up on the block, and that's the reaction force. Now, if I started to apply an active force to the block, like pushing or pulling on it, and the block didn't move anywhere, I know that there must be a force reacting in the opposite direction that is exactly equal to the force I'm applying, and that's another reaction force. And we call that reaction force friction. What happens to friction as I increase the pulling force? Well, as the pulling force increases, the friction increases because it's reacting to the force I'm applying. And if I want to move the block, I have to overcome, or I have to apply a force greater than the maximum value that friction can take. So if friction stops moving and I still apply more pulling force, like this, what do you think is going to happen to the block? Well, the block's going to move, just like that. And it'll move in the direction of the force that I'm applying. Now this is really handy because it means we can actually measure the maximum value that friction can take by applying a force to an object right up until just before it moves. So we're going to measure some friction values with the little force meter we made. Now what I've done is I've switched around the elastic band. I've literally just pulled it round into the back so that I can read the ruler on the top, and I'm going to hook this into this little plastic pot I've made a little hole so that I can just pull it along like this. And then I've got some apples and clementines in there just to give it a little bit of weight, so it's a little bit harder to move. And what we can do is we can record some friction readings. So all we're going to do is pull it very gently, and we just keep pulling. We can see the force is going up, so the elastic band is beginning to stretch. And then as soon as the elastic band starts to move, that's when we want to take a reading. So for this one, it's occurring about 4.3 centimetres. So I just write down 4.3 centimetres. Don't worry, we'll convert that into force, into a force reading, using the calibration graph that we had from earlier. Now I've got a whole load of different materials. A bit of paper here, so if I put some paper on the table instead, and I hold on to the piece of paper here, I can just pull very gently until that's 5 centimetres, that one. I've got a cloth. It's all just some different things for you to measure some forces. So this is going to be a bit of a trickier one to measure because it's going to jump a little bit. Oh, no, there we go. Oh, that's about 5.1. 5.1 centimetres. And I'm just measuring off the side of this meter. Oh, no, I still need to have that in. Oh, dear. Getting ahead of myself. So we can put the towel down, the cloth down. Now I've got a really abrasive towel. This is an old towel. It's good for the beach, but not much else. And I can put that on, make sure the paper clip's in the centre of the elastic band, and then I'm just going to pull it along like we did with the others. Oh, that's about 5.4 centimetres. And then I've got a fun one. Now this is a little bit messy. Well, I've taken it out again, and I shouldn't have taken it out. Let's just put that to the side. And what I'm going to do, now this is a wood surface, I'm going to put a little bit of fairy liquid on it. I'll clean it up afterwards. But I'm just going to put a little bit of fairy liquid on it. And I'm going to want that whole base to interact with the fairy liquid. And then I'm going to pull and see if we get a different reading. There we go. That's actually taken quite a bit. So that's gone from being 4.3 to 5.0. So that's gone to 5.0. So we've measured a whole load of distances that the elastic band was drawn on our little force meter. So let's convert those into forces, and we'll do that using the calibration graph. So we can take the values of the distance that the elastic band moved and use them to measure the force that we had to apply to overcome friction. And how we can do that? Well, if I take the first value with the distance of 4.3 centimetres for the table, when we were pulling across the table, and I can see that if I draw a neat line from 4.3 to my fitted line from the calibration curve, and then I go down from that line, it equals 3 newtons. So 4.3 centimetres of the elastic moving in my force meter is equal to 3 newtons of force. So friction is just an ever so slightly bit less than 3 newtons because we were moving at that point. So we'd overcome it. Now we can just have a quick look at some of these values, and with the table we can see it was the lowest. So it was the least friction for the table. With a towel, it was highest. 3.8 newtons required to move it. And interestingly, with the washing up liquid on the table, it was actually higher than just the table by itself, wasn't it? Because the washing up liquid actually made it a bit sticky, a bit harder to move. So where does this friction actually come from? Well, in order to answer this question, we have to really look in a bit of detail at the block and the table. So if we zoom right in and imagine we're looking at that interface between the block and the table, we can see that there's a line here where the block is touching the table. Now I've drawn this beautifully smooth, but in real life it's not beautifully smooth at all. It's maybe better represented a bit like this, with lots of little nodules sticking up and lots of little pits and dips sticking down, where the surface, these are tiny little changes, but can interact and rub across each other. Now, I will tell you this is a very simple explanation of friction, because really, if we want to get into detail, we want to think about how molecules interact. But a simple way to think about it is that if I try to apply a force, a pulling force now, against this interface, where there's all these little bits sticking into each other from the block and the table, then I have to pull against all the little bits where the table is pressing up and catching on the block, and I have to push against all the bits where the block is interacting with the table. And the net result of all these little interactions is friction. So that's where it comes from. Now I'll reiterate, this is a very simple way of understanding it, that these surfaces are rough, and as a result they have lots of little catching points where they interact there. If you want to get into lots of detail on the understanding of this, you'll want to look into the chemistry of these surfaces. So let's see what we can use this for. So we understand how to measure the maximum value friction can be, but what can we do to increase that value of friction? Well, there's a really nice little trick, and I'm sure you've seen this done before, but now we're going to explain it, which is, if I have two pieces of paper, I've just got two sheets of paper here, it's relatively easy to slide them over each other, it doesn't take much energy, and I can do it really easily. But what happens if I start putting pages together? So if I had these two magazines and I just started interlocking the pages, well, this is easy. I can pull those apart because it's only one piece of paper interacting with another piece of paper. But now if I do it again, that's two interactions, that's three interactions, that's 4, 5, so I'm additively adding up the friction maximum. And that's going to create something that's really, really hard for me to separate. So, let me have a go with this, and then we'll have a go at pulling them apart. Two interlocked magazines. It's about 200 pages. So that means the friction maximum is going to be almost 200 times just two pages interacting and rubbing against each other. Now I should be able to just about pull these apart, but it's going to take a lot more effort, and I have to be careful I don't wiggle them, because if I wiggle them they'll work free. So what you want is good contact between the pages before you pull. There, can you see? I put a lot of tension into that, and it's not coming apart. Because all those bonds, all that interaction between the sheets of paper, it's very, very hard to pull apart. Well, I hope you enjoyed that. That's a good one to try on a family member. You fold it up and see if they can pull it apart. Thank you so much for watching. I hope you enjoyed this, and I hope it made a bit of sense of friction. If you did enjoy doing this experiment, there are lots of other ones you can do. You can alter the mass in the little container and see how that affects it. And you can also alter the surface area that the mass has with the table by using a bigger container or a smaller container, and see if that has an effect. If you like this project, why not have a look at some of our other projects? Thank you so much for watching, and see you next time.